Okay, so welcome back, everybody. I believe this is week 8 of class now, so we're pretty deep into the semester at this point. And what we're going to do today is continue our discussion of Newton's laws of motion. So in the previous lecture, we covered the first law and the second law in some detail. So we're going to wrap that up and then move on to the third law. But I want to give you a conceptual question to start off, just to see where your head's at on this stuff. So this is just a true or false statement, okay? So here's the statement. According to Newton's second law, if the net force acting on an object is 0, then the object must not be moving. So is that true? If the net force is 0, does that automatically imply the object is not moving? So let's see where you're at. Who thinks this is a true statement? Who thinks it's a false statement? Okay, so you're getting this right. Why is this a false statement?
Not accelerating.
Okay, good. So 0 net force means you're not accelerating, but that doesn't mean you're not moving, period, right? It's possible to be moving at a constant velocity and not be accelerating, okay? So we're going to go into like way too much detail on this one. It would look something like this. F equals ma is Newton's second law. And what we're saying is that in this particular case, there is 0 net force acting on our object. So that means A is equal to 0. We're not accelerating. When you're not accelerating, your velocity is not necessarily 0. That doesn't mean V is equal to 0. That just means V is constant, okay? That makes sense? Because remember, acceleration has to do with changes in your velocity that are occurring. If your acceleration is 0, your velocity is not changing, it's staying constant. So that could mean you're at rest with 0 velocity, right? If your velocity is just 0 and it stays that way, that's constant velocity. But it could also be non-zero, in which case you're just moving along at a constant speed in a straight line path, okay? So that's why the statement is false. Just means you have constant velocity, not necessarily 0. Okay, we're good on that? All right, so let's move on to something else. All we've done so far are make statements about what the first law of motion and what the second law of motion are. But in actuality, if you want to use the second law of motion in any practical scenario, you're going to have to get familiar with some of the different types of forces that are out there in the real world. So we're going to cover 2 of those, which are weight and normal forces. Okay? So we're going to start by talking about weight. And I think the best way to introduce the topic of weight is to compare it to something else, which is mass. And to make the note that these are not the same thing. Mass and weight are not the same thing. They have different meanings, and let's see why that's the case. Okay, so let's start with mass. Let's, try to actually define this thing. We haven't really defined it. We've just said that it's a term in the equation F equals ma, but we haven't really said what mass actually is. So mass, in the context of Newton's laws, is a resistance to being accelerated. That's the way you want to think about mass. So the more mass an object has, the harder it is to get it to accelerate. In other words, the more force you're going to have to apply to it to get it to accelerate. If an object has low mass, it's very easy to get it to accelerate. That's the meaning of mass, okay? So you have to give it a very hard push to get it to accelerate if it's a high mass object. And you can actually see that this is the case just by looking at the equation F equals ma. I'm going to write the equation not symbolically but in words. Force equals mass times acceleration. Just look at that equation and solve for mass, okay? Mass is force divided by acceleration, okay? So again, this is what I was saying. If you have a large mass, that means it takes a large amount of force to get it to accelerate in some way. That's how you want to think about this in the context of Newton's laws, okay? Okay, so for mass, what do we measure this in? Kilograms, because that's our SI unit. And one thing to note about mass is that it's what we call an intrinsic property of the object, okay? So if you have a certain mass, let's say 80 kilograms, just to pick a number, that's your mass if you're sitting here on Earth. That's your mass if you're floating out in the middle of space. That's your mass if you're standing on the moon, right? It doesn't matter what the context is. Mass is just a property of the object. It doesn't depend on what kind of environment you place that object in, okay? On the other hand, weight is a very different thing. Weight is the force of gravity that's pulling down on an object, okay? So mass is not the same as weight because weight is a force, in particular the force of gravity. So we measure mass in kilograms because weight is a force. We measure that in newtons, okay? And it's really important to see that weight is not an intrinsic property of an object because the force of gravity that's acting on you depends on where you are, okay? If I'm standing right here on Earth, the Earth pulls me down with a certain gravitational force. If I were standing on the moon would be pulling me down with a much smaller gravitational force. And if I was floating in the depths of space, basically far away from any objects, my weight would basically be zero. There'd be no gravitational force acting on me. So it depends on where I'm at, where I'm located, what my weight is. We often confuse these two things because normally we're talking about standing on the surface of the Earth, but it is important to note that these are different things, okay? So do we have any questions on that distinction? So mass and weight are different. So to illustrate this difference, let me show you the equation that we can use to calculate an object's weight. Okay, so mass is just m measured in kilograms. How do we take that and then calculate an object's weight? It's given by this formula right here. Weight is just m times g. You take the mass of the object, and then you multiply by g, which is the acceleration due to gravity. And of course we know that g is 9.8 meters per second squared if you're standing on the surface of the Earth. But again, I want to point out that g takes on other values on different bodies. So for example, let's just look in this table real quick. If you're standing on the moon, g is 1.62 meters per second squared. So objects on the moon accelerate much slower than objects in free fall on Earth. And that affects the weight because we're plugging in a smaller value of g there, right? About 6 times less. So if you're on the moon, you weigh about 6 times less than on Earth, but your mass is the same, okay? So it's g that's changing, mass is staying the same. Okay, one other quick note about this. When we use this constant g, 9.8 meters per second squared, we kind of act as if it has the same value everywhere on the surface of the Earth. Strictly speaking, that's not true. G can vary slightly depending on where you are and also how high off the ground you are. Turns out G gets weaker as you go up in elevation. Usually this is not something that's noticeable, but it is an effect, okay? So the takeaway here is weight is given by mg, and g is something that can change depending on where you're located. So that's why weight is not an intrinsic property of an object, okay? Do you have any questions on that? All right. So here's a couple things for you to try out to calculate. So we have a bowling ball with a mass of 5.5 kilograms. What is the weight of this bowling ball on Earth? Now, in the SI system, we measure any type of force, including weights, in units of newtons, right? But what I want you to do is do this in units of pounds, okay? So what you'll do is first calculate it in newtons, and then use this conversion factor to go between newtons and pounds. 1 newton is the same as 0.225 pounds, right there. Okay, then do this same calculation. What is the weight of the bowling ball, but not on Earth, on Pluto, where g is 0.42 meters per second squared. It's a lot weaker gravity on Pluto. And again, try to convert that to units of pounds. So see what you get, and then we'll go through it together, okay? Take a few minutes to work this out. Just remember, weight is m times g. So that answer in newtons. All right, let's go through this one together. Okay, so what we're calculating here is weight, which is a force, and like any force, it's a vector, so we call that vector W. But we just want the magnitude of it, just how strong is that force. So that's just mg. By the way, the direction, it's down, right, towards the ground. All right, so if we're on Earth, and we have this 5.5 kilogram bowling ball, its weight is 5.5 kilograms times 9.8 meters per second squared, because that's the value of g on Earth, okay? And what does this work out to? Someone tell me? 53.9. What did you say? Oh, 53.9, yeah, okay. And the units here are kilograms times meters per second squared, but what is that equivalent to? That's the same as saying 53.9 newtons, okay? Actually, we want to just keep 2 sig figs on that, so let's keep track of that. So again, newtons is the SI unit for force, but just for fun, we're going to calculate that in pounds, because that's something you might be more familiar with on a sort of day-to-day basis. So 53.9 newtons, if we convert that to pounds, just use the factor. 1 newton is equivalent to 0.225 pounds, which is LBS. Newtons cancel, so how many pounds are we talking here? 12, yeah. So if you have a 5.5 kilogram bowling ball on Earth, that's going to weigh 12 pounds. But let's do the calculate. So this is on Earth. Okay, on Pluto, we have m times g, which is 5.5 kilograms. Remember, the mass doesn't change. Whether we put the bowling ball on Earth or on Pluto, it's an intrinsic property. But g is what changes. It's 0.42 meters per second squared. So that's telling us that gravity on Pluto is much weaker, over 20 times weaker than it is on Earth. And for that reason, things are going to weigh a lot less. Okay? So what does this work out to?
2.31.
Yeah, so that's 2.31. And as we saw, the units are newtons, right? So we're just going to go right ahead and convert that over to pounds using the same conversion factor. 0.225 pounds equals 1 newton. So cancel out newtons, we're left with pounds. What do we get?
0.52.
0.52. So on Pluto, that same exact bowling ball only weighs about half a pound. Okay? So, any questions about how this works? Hopefully pretty straightforward. Okay. So what is it? Okay, so the weight is different because the force of gravity is different. The mass is the same because that bowling ball is just as resistant to being accelerated regardless of where you put it. So it's just as hard to push the bowling ball around regardless of where it's at, okay? Okay, so we covered weight, which is the downward pull of gravity acting on an object. Now let's talk about normal forces, okay? Has anyone encountered this idea of a normal force before? Is this something you've encountered at any point? Okay, there's a normal force acting on you right now. It's the entire reason you're not just falling through your chair and falling through the ground. Because of course, if gravity pulls you downwards, right, there must be some kind of other force balancing that out so that you don't just free fall downwards, right? So that's a normal force. That's what we're talking about. Let's take an example of something simpler than a person, because you have a lot of points of contact with the chair and with your, the sides of the chair. Let's just say we have a block resting on a table, something that simple. Okay? And let's draw a free body diagram of that block. Remember, a free body diagram is just something that shows us all the different forces acting on that block. Okay? So of course, we know there's a downward force W, that's the weight or the force of gravity acting on the block. Okay? We also know that if a block is just sitting on a table, it shouldn't be accelerating, right? There shouldn't be any up or down acceleration, which means that force has to be balanced out by something else. It has to be balanced out by an upward force that has the exact same strength, but is pointing in the opposite direction, so it cancels it. And that force is what we call the normal force, okay? What is that force? That's basically the force that the surface of this table is pushing up on the block with. That's an example of a normal force. But actually, normal forces are a lot more general than that. You have normal forces anytime two surfaces are pressed against each other. So here, if I just do this, I push my hands together like this, I have normal forces between the two surfaces that I'm pressing together, right? If I press my hand down on the table, there's a normal force. If I press my hand against the wall like this, there's another normal force. Just whenever two surfaces are pressed together, you get these normal forces, okay? So let's take a look at how this works. Normal, in this context, the reason that word keeps popping up is normal is just synonymous with perpendicular. Perpendicular to the surface. This is how you want to think about this. So the direction is perpendicular to the surface. All right, so you have two surfaces in contact. They exert normal forces on each other, and we just indicate that those forces are perpendicular to the surface, okay? Now, the other thing to note about these normal forces, again, this is a good example, just press your hands together. The amount of normal force is telling you how hard the surfaces are pressing together, right? So if you push your hands together lightly so that they're barely touching, there's a small normal force. If you push them together really hard, you have a bigger normal force, okay? If I actually lose contact like this, the normal force goes to 0. The normal force is a contact force, so if two objects lose contact, any normal force that there might have been before goes to 0. Yep.
What would that have to do with maybe a spring that you're pushing against that might push against?
Yeah, so we're not really going to get into this right now. If you take 45 and 47, you'll start to explore these ideas a little more. But yeah, essentially, a solid piece of material can be thought of as a bunch of little springs. Like when I push the surface down, you might not even see it, but I kind of do deform it a little bit, much like I deform a spring when I press against it. So the kind of physics that describes how springs deform can be used to describe how materials deform, but it's a little beyond the scope of what we're going to do here. So yeah, I'm going to say a very simplified version of what you asked about, I think. what is the physical origin of normal forces? Why is it that when two surfaces are in contact, there's some kind of force between them? That's something we want to understand, right? So ultimately, normal forces occur because of repulsion, electromagnetic repulsion between the atoms on each one of those surfaces. So, for example, if we take a look at a book resting on a table and then zoom in to the atomic level so we can see like all these different atoms that constitute the underside of the book and all these different atoms that constitute the table surface, there's going to be contact between these two, right? And it turns out at the atomic level, there are these electromagnetic forces that repel atoms away from each other. You can't just push two atoms together until indefinitely. At some point, they're going to start repelling each other, and that's the origin of these normal forces, okay? So the two surfaces are just pushing away from each other, right? And that's what's happening when you sit in your chair, preventing you from falling through the floor. That's what happens when anything sits on a surface and doesn't fall through that surface, okay? So normal forces, again, are perpendicular to the surfaces of contact. Later on, we're going to learn about this in the next chapter, but I'm just going to give you a preview to it. There's also something called a friction force, which is very much related to what we're talking about here. A friction force is parallel to the surface. Okay, so let me give you another example of this, right? So again, you push your hands together. The normal forces are perpendicular to the surface of my hand, basically. So, for example, pushing my hands together, this hand is exerting a force going in that direction on this hand. Does that make sense? Now, if instead of just pushing your hands together, you try to like slide one past the other, like this, there's going to be friction that prevents that motion from happening, okay? Or at least slows it down. That friction force doesn't act perpendicular to the surface of my hands, it acts parallel to it. So that's what a friction force is. And we'll learn about that a little bit more in chapter 6. Okay? So any questions so far? All right, I'm going to give you an example. So we have a 2.5 kilogram book resting on a table. And so what you do is you come along and you push the book down. So you push down on the top of the book like this with a force of 15 newtons. So my question for you is, what is the magnitude of the normal force between the table and the book when you do that? Okay, so here's what I would start with. Draw a free body diagram of the book. Show all the forces acting on it. Can we just list those off real quick? What forces are acting on this book in this scenario?
The table.
So yeah, the table is exerting a force on the book. That's the normal force that we want to find. Yeah? What direction is that going in?
It's going up.
Yeah, so the table, remember it's perpendicular to the surface, it's going to be pushing up on the book. That's the normal force we want. What else is happening? Someone said it? There's the weight. So gravity is pulling the book down. And then, of course, what's the other force? Just whatever force we're pushing with, right? So there's our pushing force, the normal force, and the weight. And what can we say about how those forces add together?
Equals or up.
Yeah, because the book is just resting there and it's not accelerating. Okay, so based on that, you should be able to solve for the normal force. All right, so try drawing that picture, the diagram of the forces, and then try using that to solve for the normal force. Let's see what you get. Okay, good. I think some people have this. Let's go through it. And then I'm going to ask you a follow-up that's kind of a variation on this. Okay? All right, so start with this. Anytime you're going to do a problem involving Newton's laws, it's pretty much guaranteed that you're going to at some point draw a free body diagram because you want to have a good accounting of what the forces are, right? So like we said, there's the weight. This is the force of gravity that pulls down on the book. We also have the force that you're pushing with, so I'm just going to call that P. Because you're pushing down, it's going to be a downward arrow. And then the normal force from the table is going to be going up. And I'm drawing that arrow a little bit bigger because I already know it's going to be a larger force than either of these two, okay? So using this coordinate system where the y direction is up, we're going to go ahead and apply F equals ma to the y direction. Remember, when it comes to Newton's second law, we can always break it down by component. And in this case, there's simply nothing happening in the x direction, so we could just focus on y, okay? So on this side of the equation, ma, what do I write?
2.5 kilograms times gravity.
Okay, so you want to be careful. Ay is actually just equal to 0 because there's no motion. Okay, it's not in free fall, it's just at rest, okay? So on the right side of the equation, we simply put 0, okay? Now on the other side of the equation, we have to say how these forces add together. Now, in this case, it's pretty simple. Anything that's pointing up just gets a positive sign because it has a positive y component, and then anything pointing down gets a negative sign, okay? So here's how it goes. I'll add the magnitude of the normal force, then I'll subtract the magnitude of my push force, and then I'll subtract the magnitude of the weight, and all that equals 0. Okay, so we're saying these forces added together give you 0. So what am I trying to find? The normal force, right? What's that? Well, I solve for it, it's just these two, P and W, added together. It's the magnitude of P plus the magnitude of W, okay? Does that make sense? And again, the magnitude of W is just mg, because it's the weight. So there you have it. So now we can put the numbers in. The force that I'm pushing down with is 15 newtons, right? The mass of the book, m, is 2.5 kilograms, and g is 9.8 meters per second squared. And of course, kilograms times meters per second squared gives me newtons, which is the same unit here, so we can add these together. What's the result of this? What do we get?
9.5.
Yeah, 39.5 newtons of force. So in other words, the normal force is greater than the weight of the book. So normally, it would just equal the weight of the book if you weren't pressing down on the book. But since you are, you're increasing that normal force. That's what we see here. That make sense? All right, any questions on how we did this? All right, then we'll keep going. So this is a variation on what we just did, okay? In this case, we have a book resting on the table, and instead of coming along and pushing down on the top of the book, we pull up on the book a little bit, but not enough to actually lift it off the table. Okay, so you can imagine having some object sitting on the table, and I'm pulling up on it, but I'm not pulling up with enough force to actually lift it off. Okay, so in that case, what is the normal force? Try to figure that out. It's just a slight variation on the steps we took to do the last one. Okay, so I see some people are starting to get this. That's great. And I think for a lot of you, you just kind of can skip some steps and jump to the answer, but what I want you to get used to is being really methodical in how you set these problems up, because once the problems get more complicated, it's really going to be important to have everything clearly laid out on the page, okay? So here's what's changed. Our free body diagram looks different now. We have the weight going down, that doesn't change. We have the normal force going up. The table always is going to push up on the book. But instead of pushing down, we're pulling up. So the force P, I'm going to show that going upwards now, okay? That's what's changed. And what we're doing is pretty much the same as before. We're saying F equals ma applied to the y direction. And, okay, for the acceleration, we have 0 for the same reason as before. There's no motion happening. And when we add up the forces, now here's how it works. We have two different forces going up, which are N and P, and we have one force going down, which is W. So when I add these together, here's how it works. I have positive magnitude N plus magnitude P, because those two are upwards, and then minus magnitude W. That's how I can add these together. And by the way, you could put like, what, sine of 90 degrees in here, but I'm kind of skipping over that, right? You can clearly see it's just add these two together, subtract this one, right? So to solve for N, in this case, we have the magnitude of W minus P. That's how it works now when we solve for N. So that's mg minus the magnitude of P, which is 2.5 kilograms, once again, times 9.8 meters per second squared, and then minus, what was our force we're pulling up with? 15 newtons. And then what does this result in? Yeah, so that results in 9.5 newtons of force. So it makes sense. We're actually reducing the normal force between the book and the table by pulling up on it, because they're pressed together less hard than before, right? So, any questions on that? Okay. All right, so we talked about the second law of motion, and of course the first law, and then we talked briefly about weight and normal forces, okay? So we're going to introduce some other types of forces and how to deal with them as we go on. But at this point, I think it's important to get to the third law of motion. Now this one is a little bit subtle. It's kind of like the first law. It's pretty simple to state what it says, but to really deeply understand it, it's a little bit more subtle. So let's get into this and do plenty of examples, so hopefully we get the idea. Okay. I'm going to pose a kind of weird question to you, but just go with it. Let's say that you find yourself in a very large room, and the floors in the room are completely frictionless, which basically means you can't walk, right? Because if I try to walk, my foot's just going to slide over the floor, and I'm not going to move, okay? What you need to do is escape from this room, and the door is far away. It's like 45 meters away, which means you're going to have to propel yourself over there somehow, right? But you're too far away from any of the walls in the room, so I can't just go to a wall and sort of like push off and then slide on the floor to get to the door. Can't do that. I don't have any tools either. I don't have like a grappling hook or a lasso or anything like that. I just have me and nothing to push off of. Can't push off the walls, I can't push off the floor because it's frictionless. So is there any way to get out of this room? That's my question for you.
You throw something behind you.
Okay, that's getting close to what the answer is, but technically we don't have any stuff to throw. Yes?
You could try like blowing.
Perfect. Yeah, just blow some air out. Think about it, right? So let's say that's the door I'm trying to get to over there, right? So I'll face away from the door, blow some air out this way, and now I'm kind of acting like a rocket, right? I'm propelling myself backwards, and I can get over to that door. So yeah, that's exactly right. And if we want to understand how that's working, it involves Newton's third law. Okay? So let's draw a picture of this situation. Right here is our floor, which is completely frictionless, which means we can't walk on it. Here's the door we're trying to get to, and then here's us. Okay, so if we blow some air out this way, that means you are exerting a force on the air in this direction, okay? So I'm going to write this out in a really verbose way. Force of the person on the air. So the air is feeling this force. Make sense? The idea is that force doesn't just exist in isolation. There's something called a reaction force that happens. If you exert a force on the air this way, guess what? The air exerts a force back on you in the opposite direction. So this is the force of the air on the person. And these forces are equal and opposite. This is what the third law is all about. Okay? Is that forces always come in pairs like this. And you can use this reaction force to propel you backwards and get to the door. Okay? If there was no air in the room, you'd be in trouble, but you'd also not be able to breathe, right? So, okay. Any questions on that? All right, so that's just an illustration of the third law. So let's get into it and what it's really saying. So there's a lot of ways you could state the third law. This is the most maybe common expression that all of us have probably seen before. Every action has an equal and opposite reaction. We've all heard this kind of statement before, hopefully. So oftentimes this is used kind of metaphorically, but it actually has a physical meaning. And let's get into that. This is kind of a more physics definition of the third law. So let's say we have two objects, A and B. They can really be any two objects at all. If object A exerts a force on object B, then object B must also exert a force of equal magnitude and opposite direction back on object A. Okay? So if one object exerts a force on another, that other object exerts a force back on the first one. They come in pairs like this. So here's kind of an illustration of that idea. In this case, we're going to imagine that object A and object B are just two blocks. And one thing we can do with two blocks is kind of push them together, right? So where they're making contact right here, they're exerting forces on each other, right? Okay, so here's some notation that we're going to have to get used to for the third law of motion, okay? If you see a force labeled like this with two subscripts, it's telling you something. It's telling you which object is exerting the force and which object is experiencing that force. Okay, those are two different ideas, right? So in this picture where it says FAB, what this means, this is the force that object A exerts onto object B. So you see when B is the second subscript, that means this is the object that is experiencing the force, okay? Okay, over here, it says FBA. What does that mean? That means the force that object B is exerting onto object A. Because A appears as the second subscript, what that means is object A is experiencing that force. So these two forces are equal in magnitude. They're just as strong as one another, but they point in opposite directions, right? And we can pretty much intuit this, right? If I were to push two blocks together, this block would be pushing this way on this block, which is the force FAB. And at the same time, this block would be pushing this way, which is the force FBA. So one way to say that these are equal in magnitude but opposite in direction is to say that between the two forces, there's a minus sign. So FAB is the negative of FBA. And this is true of any two pairs of forces between two objects that are interacting. Okay, so it's completely general. So, do we have any questions about this? What this is saying? We'll go through some examples to make sure it's clear, but anything so far? Okay. So I'm going to give you an example of the third law. I'm going to show you an animation, a slow motion, it's actually just a video, of a pool ball hitting the side of a pool table, okay? And it's going to, of course, go in and then bounce off the pool table, okay? So let me ask you this. If this ball comes in, it hits the side of the table and then bounces back, what direction is the force that's acting on this ball to get it to bounce that way? So if it goes from moving to the right, and then suddenly it's moving to the left, what kind of force, what direction is the force that's acting on it?
To the left.
Yeah, you see that? This ball must be experiencing a pretty big force to the left if it suddenly changes its motion this way, okay? But at the same time, the ball is exerting a force on the table, right? What direction is that force? It's to the right. And you can see that because when it hits the table, it gets deformed. It gets deformed in this direction, indicating there's a force acting on it to the right. So you can very clearly see this happening, right? Okay, so the force that the table exerts on the ball, that way. The force that the ball exerts on the table, that way. Equal magnitudes, opposite directions. That's the third law, okay? I guess I told you what the directions were up here, okay? But there it is. Any questions on this example? Okay, here's another one. Walking. Right? Have you ever thought about the physics of walking around on a surface? I mean, it wouldn't be possible without the third law. Have you ever given it any thought, if you're walking or running, if you want to go forward, you push backwards on the ground, don't you? If I want to jump that way, I'm going to push backwards on the ground to make myself jump that way. That's just the third law, right? Because this is a free body diagram of the person's foot and the ground when the person's walking on the ground, right? So the person's foot is pushing backwards. That's this red arrow. That's the force acting on the ground from the foot. You're pushing back on it. But as a reaction to that, the ground pushes forward on your foot, and that's what it allows you to actually move forward. Okay? So you need this action-reaction sort of pair for walking to even be possible. Okay? And really any kind of motion, if you think about it, right? If I want to propel myself forward by pushing off this wall, right? What direction am I pushing the wall to go forward? I'm pushing it backwards. I'm pushing the wall this way. The wall's pushing me that way, right? Okay, so hopefully you see the idea. So related to that, here's a conceptual question. You and your friend are standing on a sheet of frictionless ice. So you're just in a very low friction environment. So don't worry about friction. You're just standing still at the beginning. And let's just take note of the fact that your mass is less than the mass of your friend. Your friend has a bigger mass. So if you go ahead and push your friend, so you push your friend like this, what happens? Is it that your friend slides to the right, you slide to the left, or both of those things happen at the same time, or that nothing happens, no one moves?
Slide to the left.
You can see.
So what do we think? A? B? C? D? It's C, right? You can't push your friend without your friend pushing back on you. That's the whole point, okay? And so, what's the direction of the forces involved here? The force that you exert on your friend, that's to the right. And that causes your friend to start moving to the right, okay? The force that your friend exerts back on you, that's to the left. And that's going to cause you to start moving to the left. Even if it's just you that's exerting any energy or any effort, that's still going to happen. Just like I'm the one exerting effort to push the wall, but guess what? The wall's still pushing me back. That's just the third law. Okay? So does that make sense? So you're both going to move in opposite directions because you're exerting forces on each other in opposite directions. Okay? Go ahead.
Question though, would your friend move like also the same distance as you exactly, or would they just
Yeah,
be
so-
less?
Yeah, that's you're anticipating the follow-up question. So yeah, just because you both start moving, what about the speeds? So same scenario, right? You're the less massive one, your friend is the more massive one, and you push your friend. So at the moment when you let go, you're both sliding away from each other, correct? So what statement is correct? Who's going to have a greater speed when you let go? Is it you, your friend, or will you be moving away at the same speed? So give this a little bit of thought, okay? So try to think about the third law of motion and the second law of motion at the same time in this scenario to see who's going to be moving faster at the end of this process, okay? So take a minute, think it through. Maybe even jot a few notes down, and we'll put it to you. All right, so who says it's A? B? C? Okay, so I think conceptually you get this. You're the one who's going to be moving faster because you're less massive. Okay, that actually matters. And I'm sure a lot of you can kind of just intuit that's the answer, but I'm going to go through way too much detail because it's important to start using these sorts of notations and formulas, okay? So here we go. The situation looks like, oops, what am I doing here? There we go. The situation looks like this. So here's you, the smaller one, and here's your big friend, okay? Okay, so this is you, and this is your friend. So I'm going to draw a force acting on your friend, which I'm going to label as FYF. What does that mean? That's the force that you exert on your friend, of course, right? And then the reaction force to that is the force that your friend exerts on you. So both of these forces are happening at the same time. And according to the third law, they're equal magnitude. And of course, they point in opposite directions. We're already showing that, right? So the magnitude of the force that you exert on your friend is equal to the magnitude of the force that your friend exerts on you. Okay? That's how we can really compactly make that statement, okay? Are we all clear with the symbols here? Okay. Notation is kind of important. Okay. So for the force that you exert on your friend, let's now introduce the second law. Because this should equal the mass of your friend times the acceleration of your friend, right? And this force that your friend exerts on you, that should equal your mass times your acceleration, right? Because these are forces acting on you, so they equal your mass times your acceleration. So if we look at your acceleration and we solve for it, that's your friend's acceleration times the mass of your friend over the mass of you, right? And this means because the mass of your friend is bigger than the mass of you, that your acceleration is bigger than the acceleration of your friend. So, in other words, there's the same amount of force being applied to you and your friend, but because you have a smaller mass, for the same amount of force, you're going to accelerate faster. Okay, that's basically what's happening here. So you accelerate faster, you will be moving faster at the end of this process. Okay? That's how we can really rigorously show this. So, any questions on that? All right, so we'll keep going. More conceptual questions. Okay. Here's a paperclip. Here's the entire Earth. Okay? Of course, we understand that the Earth pulls down on the paperclip with a force of gravity, which we know how to calculate actually now. But we also should have some sense that the paperclip is pulling on the Earth with some force too, right? So what's the statement that's correct? Which force is greater in magnitude? Is the paperclip's gravitational pull on the Earth greater? Is the Earth's gravitational pull on the paperclip greater? Or is it that the two forces have the same magnitude? So what do we think? Well, who thinks it's A? Who thinks it's B? The Earth's got to be pulling harder on a paperclip than the paperclip's pulling on the Earth. Who thinks it's C? Okay, so yeah, it is C. This is kind of a trick question because I already kind of told you this is supposed to be the answer, right? Does that feel wrong though? I mean, did anyone answer C and then think, yeah, I think that's the right answer, but it kind of feels wrong? Yeah, why is that? Because of course, like the paperclip has like no effect on the Earth whatsoever, right? But the Earth has a really big effect on the paperclip,
And that
right?
has to do with like its force going against the Earth. I'm sorry, against gravity, right?
Actually, it has to do with the fact that the masses are so different. It's kind of like the one we just did, right? Even though the force is the same, if one object is just way more massive than the other, it's going to be affected a lot less by that force. It's going to have a smaller acceleration, in other words. So let's just go through that real quick, okay? Get used to the notation that we use. So here is a paperclip, and here is the entire Earth. So we'll draw some forces. This is the force that the Earth exerts on the paperclip. This is the force that the paperclip exerts on the Earth. Okay? And according to the third law, if we really believe that this is true, oh, sorry, let's put this down a little bit. According to the third law, we have to believe that the magnitude of the force that the Earth exerts on the paperclip is just as big as the magnitude of the force that the paperclip exerts on the Earth, right? But we do what we did in the last problem, and we apply the second law. Okay, so Earth on paperclip, that's going to be the mass of the paperclip times the acceleration of the paperclip. Paperclip on the Earth, that's going to be the mass of the Earth times the acceleration of the Earth. And just for simplicity, we're assuming that nothing's going on except the Earth and the paperclip interacting. Of course, in the real world, there are a lot of other forces going on, but for now, we're just going to imagine it's just these two forces. Okay. So let's solve for AE. That's the acceleration that the Earth experiences as a result of this interaction. Well, that's going to be the mass of the paperclip divided by the mass of the Earth times the acceleration that the paperclip experiences. The acceleration the paperclip is going to experience is just 9.8 meters per second squared, right? Does anyone have a good estimate of the mass of a paperclip, maybe in grams?
2 grams.
Yeah, 2. Let's just call it 1 just to be simple. But yeah, like it's in that ballpark, right? A couple grams maybe. Depends on exactly the size. What about the Earth? The mass of the Earth. Anyone? This is probably not a number you just know from everyday life, but it's something like 10 to the 25 kilograms. 10 to the 25th power kilograms, right? So the ratio of these masses is giant, right? Because for a paperclip, we have about a gram, which is 10 to the minus 3 kilograms. Whereas for the Earth, we've got about 10 to the 25 kilograms. So that's telling us that the Earth accelerates 10 to the minus 28 times the acceleration of the paperclip. In other words, it's just absolutely tiny compared to the acceleration of the paperclip. In other words, even though the forces are the same, the paperclip is very much affected by the force because it has a small mass, whereas the Earth, because it has such a gigantic mass in comparison, is barely affected at all by this. Okay? So that's how we square these two ideas. All right, do we have any questions on that? All right, so it's just like you and your friend, except you have a mass of 1 gram and your friend has a mass of 10 to the 25 kilograms. Okay? So, all right, so we're going to do some free body diagrams now, okay? In this problem, we have a stack of blocks, A, B, and C. And what we're going to do is make a very, very detailed diagram of the 3 blocks using the notation we just learned about. Remember, we have 2 subscripts on a force. The first subscript is telling you what object is exerting that force. The second subscript tells you what object is experiencing that force, okay? So it's just 3 blocks, A, B, and C, and a stack resting on a table. What we're going to do is draw the free body diagram of each one, okay? And the subscript E is going to be used for Earth. T is going to be used for the table that they sit on once we get to that. So we're going to start from the top. Let's look at block A up here. Can anyone just tell me in words what forces are going to be acting on block A? Yeah, so there's a weight, and if we want to get fancy and label this with subscripts, it would be the weight that the Earth exerts on block A. The force of gravity is exerted by the Earth itself. That's why that comes in. And then there's a normal force pushing it up, right? What is exerting the normal force on block A? It's just block B that's exerting the normal force, because it's the surface of block B that's in contact with the surface of block A. So here's how we write that, okay? We have a downward force, WEA. That's the Earth exerting this force on block A. And then we have an upward force, that's NBA. That's the normal force that block B pushes up on block A with. And those 2 forces basically cancel each other out because we know that there's no motion, so nothing's accelerating, okay? The forces are balanced out in order for there to be no motion. Make sense? Okay, now let's move on to block B. Can someone tell me what forces are acting on block B? I'm sorry. Didn't quite hear that. What was that? Okay, so yeah, C and A are both exerting a force on block B. That's good. It's kind of sandwiched right between them, right? So block A is pushing down on block B from the top, and block C is pushing up from the bottom. And then what else is happening at the same time?
The weight.
Then there's the weight, right? So those are the forces, okay? We have the weight that the Earth exerts on B, and assuming the blocks are all identical, they have the same weight. So we'll draw this just the same size as the previous weight. We also have NAB. That's the normal force that A exerts on B. Let's really think about this. Block A, this undersurface of block A is pushing down on the top surface of block B. Okay? And guess what? We have Newton's third law happening right here. Because we have NBA, we have NAB. These forces are equal and opposite. You can already see they're pointing in opposite directions. But typically what we do, you see what I just did? I put this little slash here. What that means is these are equal and opposite forces, okay? We just use that to keep track of the fact that we have equal and opposite forces on our diagram, okay? All right, and then what's the last force that's missing here? What do I call it? NCB, yeah? And it has to be kind of a larger force than these two to balance them out, right? So NCB is pointing straight up like this, okay? Okay, now, let's move on to block C. Let's label all the forces acting on that one. Just list some of them off. What would they be? The weight, of course, that's going to be there. What else?
NCB.
Yeah, so block B is going to be pushing down on block C. And then what else is happening? The table is going to be pushing up on block C. That's going to be happening as well, right? So to put that all together, we have the weight, EC, is the weight that the Earth exerts on block C. And then we have NBC, that's the normal force that block B pushes down on block C with. And guess what? We have equal and opposite forces once again. You see that? NBC, NCB, those are equal and opposite according to Newton's third law. So I'll put another set of slashes. You see how it's just helping me keep track of the fact that this force right here has the same magnitude as this force right here, okay? And then the last thing we show is what's the last force that's acting here? So we'll call that NTC. It's the normal force that the table exerts on block C. And at this point, we've completed all the diagrams, okay? But are we clear on how this works, especially with the notation? Okay, you're going to have some problems on the week 8 homework that deal with this sort of thing, okay? All right, so this is the last one we'll do today. We have two blocks, M1, which has a mass of 5.1 kilograms, and M2, which has a mass of 2.3 kilograms, okay? And they're just touching each other, and they're at rest on a frictionless surface, okay? So let's say that you come along from this side, and you push block 1 with a force of 3.5 newtons. So I'm going to push on block 1, and of course, that's going to set them both in motion, right? Okay. Question 1, what is the acceleration of these blocks? Question 2, what is the normal force between the blocks? You see they're touching each other, so there must be some kind of normal force acting at that surface. And then the last question is, how long does it take to get to a speed of 5 meters per second, assuming we start from rest? Okay, so the two blocks are on the table. We start from rest. We come along and push this one with a force of 3.5 newtons. That's the scenario, okay? So let's start by making a very detailed diagram of each one of those blocks, okay? So let's start with this. Let's start with block number 1. That's the one that was on the left side. What forces are acting on that one? Well, we have, of course, the weight of that block, which is going straight down. So using the notation that hopefully is starting to click, that's WE1. And this block is also resting on a table. So there's a normal force from that table acting on block 1, so I can call that NT1. Make sense? What else is happening? Block number 1, I'm pushing it with some amount of force. I'm just going to call that P. Okay, that's just the push force. Okay? Is there anything else happening here with block number 1?
It's being pushed back by block 2.
Yeah, see, block 2 is pushing it backwards this way with a normal force, which I'll call N21. That's the normal force that block 2 pushes on block 1 with. Does that make sense? Okay, so force P, just to be clear, that's coming from your hand, and N21 is coming from block number 2, okay? So now let's draw a diagram of block number 2, and it's the same idea, we just want to show all the forces that are acting on block number 2. I'll give you 2 of them. One of them is the weight, that's just directly downwards exerted on block number 2 by the Earth, so we call that WE2. Then there's the normal force that the table exerts, call that NT2. And what else do we have? So, acting on block 2. Block 1 is pushing it, right? Which way is block 1 pushing block 2? What direction? To the right. So I'll call that N12. And right here, we have equal and opposite forces. You see that? Okay? So this is the force that 2 exerts on 1. This is the force that 1 exerts on 2. They have the same magnitude. That's what this slash means, okay? All right, cool. So, real quick, let's draw our x and y coordinates. I'm going to show you how to find the acceleration. We'll call that just plain old A for both blocks. Because of course, if they're moving together, they have the same acceleration, okay? So when it comes time to write the acceleration for block 1 or for block 2, I'm just going to call it A, okay? And this is kind of the long route, so let's go and do it. So for block 1, what I'm going to do is apply the second law in the x direction. We don't really care about the y direction. There's only acceleration in the x direction after all, right? We're only accelerating horizontally, so that's what I'm going to focus on here, okay? The second law is F equals ma. So if we add up all the x forces, we get the mass times the x acceleration. And again, we're applying this to block 1. So I want you to look at this diagram to guide us along. What are the 2 forces, according to this diagram, that are acting in the x direction?
Push and, 91.
The force of your push and the force that block 2 exerts on block 1. But if I want to add them together, the force of the push is in the positive direction, so magnitude P with a positive sign, but then minus magnitude N21, that's how I show they're going opposite directions when I add them together, okay? We good with that? Since we're talking about block 1, the mass we're talking about is M1, and that's multiplying A, okay? Now let's do the same exact thing with block 2, okay? Let's do the same exact thing with block 2. So again, we're taking the net force in the x direction and setting that equal to A times x, correct? Okay. Now we're looking at the diagram for block number 2. We only care about forces that are acting on block 2, so focus over here. There's only one force in the x direction, right? What is it? It's N12. And it's in the positive x direction, so I have positive magnitude N12 equals M2 times A. Are we good with that? But here's the thing. By the third law, let's just make a quick note. The magnitude of N12 is the same as the magnitude of N21. They have the same strength. They're just pushing in opposite directions, right? So that means I can do the following, okay? Take the first equation I wrote down. You see how there's an N21 right there? That's the same as N12. These have the same magnitude. which is equal to this. So I can make the following substitution. I can say plus P minus M2A, that's the substitution I just made, and I can do that because of the third law. That equals M1A. So we have magnitude P equals, basically if I take this minus M2A and add it to both sides, it moves over here. So I'll have M1 plus M2 times A, which means A is the magnitude of P divided by M1 plus M2, okay? So that's just taking you through the algebra of how to solve for A, given all the different forces acting here, okay? So what do we get for A? We get the force of the push, which is 3.5 newtons, by the way. So now I'm plugging in numbers. But remember, newtons are kilograms meters per second squared. So it's useful to think of it that way. And then M1 plus M2 is on the bottom. That's just the sum of the two masses. M1 was 5.1 kilograms, and M2 was 2.3 kilograms. So this works out to, what does it work out to? 3.5 divided by 5.1 plus 2.3.
What,
0.473, and you can see that the units are meters per second squared, right? So that's how fast both blocks are accelerating. Now this is kind of the long way, as I mentioned, because can anyone see a much shorter way to do this? I could just basically act like block 1 and 2 are just a single object. So here's a shortcut. Just act like you have one object with the combined mass of M1 and M2 like this. And that's being pushed with some force P, right? If you do F equals MA on this thing, here's what you get. Magnitude of the force P equals the total mass of M1 and M2 times the acceleration. And of course, you can see that's going to give you the same answer, right? So why did we go through all this work? Well, this shortcut, it can tell us what the acceleration is. We can solve for it, get the same answer that we found before. But what it's not going to do is answer the second question, which is to find the normal force. I want to know how hard these two blocks are pushing against each other, right? And just taking this shortcut of combining the two into a single object is not going to give me that answer, okay? So here, let's go back to our equations. I have it right here. This can solve for the normal force, right? Because when we applied F equals MA to block 2, we got N12 equals M2 times A, correct? This is what we got. So if I simply plug in M2 times A, that's going to give me the normal force I need, okay? So here, I'm going to take this equation and move it all the way down here. And we have the magnitude of the normal force is equal to M2, which was 2.3 kilograms, times A, which we just found is 0.473 meters per second squared. So someone real quick, tell me what that works out to. Yeah, 1.09, correct, newtons. So that's how hard the two blocks are pushing against each other. We really need to go through all this detail to get to that answer, okay? All right, there's one last question, which is this. Remember, we start from rest, and we accelerate at this rate as we just found, okay? So the third question was, how long does it take to get up to a speed of 5 meters per second? So the last question is, find how long it takes to get up to 5 meters per second. So what we're doing here is we're combining our knowledge of kinematics, which we learned about before, with Newton's laws. Using Newton's laws, we found the acceleration, right? So if we know that acceleration, we can use it, we can plug it into a kinematic equation to answer this question, okay? And I'll just tell you what the kinematic equation is going to be. It's going to be V equals V naught plus AT in the x direction, okay? So hopefully you remember this equation, right? What is Vx? What am I putting in there? That's our final velocity, 5 meters per second, right? V naught, what's that? That's our initial velocity. What's the value? 0, because we're assuming starting from rest. Ax, that's the acceleration we found up here. That's 0.473 meters per second squared. And then t, I don't know what t is, but it's pretty simple. Just take 5 divided by 0.473, and you'll have t. And what is that? 10.6 seconds. So, by pushing the blocks in this way, it's going to take 10.6 seconds to get up to this speed. Of course, we're ignoring friction here. If there's friction involved, this all gets a little more complicated. So we'll learn about that in a couple weeks, I think. Okay? That's it for now.